I'm not recording. So this is kind of where we're headed. So let me share my screen so you can follow along. So what we did was we read in this data set. So here's the 15 trials, and here's the first card, the second card. So we have 30 cards total. We can think of these as 30 cards in a single sample, or we can think of this as 15 samples of 2 cards each. Now 2 is the minimum sample size that you can use to generate a mean, because you have to have 2 things to add together and then divide by 2. So this is the base level of sample size. And then what I asked you to do was to basically calculate the means. We saw that the means vary quite a lot. And when we calculated the mean of those means, it turned out to be 6.3, 6.4, which is pretty close to the hypothetical mean of the population, which is a mean of 7. Then we asked you to add all of these things together to get the average, which was once again 6.367, which is the average for the whole thing. That's one of the peculiarities about averages. Averages of a bunch of averages will be the same thing as the average of all of those individual values together. But that's not really what we're interested in. We're interested in how much variation there is around this. So we formed this new data frame that is all of the observations, as if we took one single sample of 30 observations. And now what we're doing is we are going through and trying to summarize this. So the first thing we did was we took sample variance. Sample variance is just the individual values minus the mean squared divided by the degrees of freedom, which is 1 minus the sample size. When we run that, we get 13.48. So now what we need to do is we need to calculate the standard deviation. The standard deviation is going to be the sample variance, which is sample var, but we want to take the square root of the sample variance, so we're going to put that in parentheses and put SQRT out in front of it, and that should give us the standard deviation, and when we check it, it should give you 3.67, which is just the square root of 13.48. Can you guys all see that? Yeah. Use your tabs to put your orange tab up if you're having difficulty. So once you type that in, you have to run it and then ask for it. Oh wait, did you run that?
This one?
Yeah. Have you run everything all the way down?
No.
Okay. Yeah. So what it's doing is saying object not found. Mm-hmm. It's because you haven't run that.
Okay,
so it's looking for that and it can't find it. So just run the whole thing all the way down to the point that you are. If you're getting an object not found error, it's because you haven't run something above it. What you got, Cole?
It's not outputting number on it.
Okay. Oh, so you ran that. Yeah, so now do stdv.
Oh.
You have to ask for it. So remember that whenever I ask R to do something, I not only run it, but then after I've run it, I call its name so that it tells me that it did what I asked it to do. Did it work? Cool. Yeah. Okay. All right. Good. Okay. All right. Yeah.
I just need people to watch.
The other thing you can do is you can also just highlight the whole page. Just highlight it with your mouse, and then just hit Command Enter, and it'll run it all. Oh. I'm not a big fan of that because sometimes there's an error in the middle of it, and then it scrams on you, and you don't know where exactly things went wrong. So I'm a big fan of executing line by line because that helps you find errors. But if you know that it works from a previous session, you can just highlight the whole thing and run it also. All right, tabs down. This is the standard deviation. What's the next step that we need to take in calculating the confidence interval? Yeah. Standard error. What's the formula for standard error?
Square root of standard deviation divided by the mean or the sample size?
Nope, it's the standard deviation divided by, you had elements of it, divided by the square root of the sample size, which in this case is 30. So it's the standard deviation divided by the square root of the sample size. Once you have done that, check to see that it did the calculation. You should get 0.67. Blue tabs up when you got it. Orange tabs if you are having difficulty. Have you not found? Did you run standard error?
Yeah.
So run that.
Line 22.
Oh, okay. Let's see. What's going on at line 22?
22, there's a typo in this.
Oh, error. Yeah, good. Yeah. Yeah, typos. It's the bane of our existence collectively. All right, tabs down. So now you've calculated the standard error. To finally get to calculating the confidence interval, what's the next thing you need to do? You have the standard error, but you need to know how many standard errors away from the mean you need to go, right? Where do we find that information? We go to the t-table. And for this, it's going to be the t with an alpha level of 0.05 because we want a 95% confidence interval. And in this case, the degrees of freedom is 29 because the degrees of freedom is 1 minus the total sample size. How many of you carry around a t-table in your back pocket? I certainly don't. Let me introduce you to a website. Go to your web browser. Type in the name Daniel Soper. When you type in Daniel Soper, you will see free statistics calculators. Click on that. Go down to, they're in alphabetical order, so down at the bottom is the t-distribution. Click on that bar. And then you have to figure out which of these things that you need. And I think it's the student t-value calculator. Yeah. So go to the student t-value calculator. So under t-distribution, it's down towards the bottom. Student t-value calculator. It will then ask you two things that you need to know. You need to know the degrees of freedom, which in this case is 29. And you need to know the probability level, which is 0.5. Click on calculate. And what it will do is it will give you what the t-statistic should be. And you want the two-value t-test, the two-value t-statistic, which in this case is 2.045. The student t calculator. It's important that you do the two-value t-test because we're testing either or. It's either higher or lower, rather than the one value, the one tail, right tail. So Blaine, it's this one right here, the third from the bottom within the t-statistic, t-distribution. Daniel Soper's website is nice because you don't normally have the statistical table that you need hanging around. But this guy has gone to a lot of trouble and effort to put these online calculators. The other thing is most t-tables, if you go and look at a t-table, which we do have access to, in your PowerPoint, there's a t-table, you will see that they only go up to 29, so you can actually check and see if his if his calculations are correct, and you see that for the 95% confidence interval, 29 is 2.045, so we got the same answer that is in the table. But the table is usually cut off at 30. And so if you have a sample size that is bigger than 30, a t-table isn't going to help you anyway, but the t-calculator on SOPR's website will do any sample size that you put in there. So you don't have to do some weird extrapolation thing.
So what does it mean by t-value right tail and t-value two?
So when you are looking at this distribution of sample means, if you are looking for how many standard errors you need to go away from the sample mean, you need both sides of the table because you want to know how much of the distribution lies within the two boundaries. So if you have 95% of the observations in here, you have 2.5% out here, you have 2.5% out here. So you have distribution density out in both tails. If you're testing a hypothesis where you don't know if it's directional or not, you don't know if you're looking for a difference where A is bigger than B or B is bigger than A, it could be that a mean is different from this mean because it's over here, or it could be that it's different from this mean because it's over here. If, on the other hand, you have a directional hypothesis, you think that the means are going to be different in a particular direction, you might say, well, I'm only interested in whether or not means are bigger than the mean that I'm comparing it to. So you can take all of this density that was down here, you can dump it into here. This then has 5% of the density, and this reduces the size of your confidence interval because you're asking a directional question rather than an either-or question. So that's the reason. So normally when you calculate confidence intervals, you do the two-tailed t-value because most questions are going to be either or. It doesn't have to be that way. If you have a directional question, then use the one-tailed. And the nice thing about being directional is you gain a little bit of statistical power because your confidence interval is narrower in that point. Because you have some a priori knowledge that you expect the answer to be skewed in a particular way. So we can find that from Daniel Soper's website. So we can basically now go back into R. What did I do with R? And now what we can do is we can just calculate the width of the confidence interval, which is simply going to be the standard error times 2.045. And then check to see that that worked. 1.37 is what I got. Is that what you guys got? Well, now we can calculate what the upper limit is to the confidence interval, which is simply going to be the mean. What was the mean? Oh, the mean is called average plus the confidence interval. When we ask for upper limit, I get 7.73. So our mean was actually 6.3667. 6.3667. And our confidence interval goes up to an upper limit of 7.74. And we can calculate the lower limit by subtracting the confidence interval range from the mean. So we can go and make the lower limit equal to the average minus the confidence interval, which then would give us 4.995. Is that right? 4.995. Is that what you guys got? Yeah.
For whatever reason, I don't think you ever put in the average.
I also don't have any.
Oh, did I not put in the average? Did you not put in the average?
I never did it.
Oh, what I did, what I did between, you probably just had total sum divided by 30. Name that average. That's the difference between yours and mine, probably. Go up to around line 13, you'll see something that says total sum divided by 30. That is the average. And then that should work for you. 4.995. All right, tabs up if you got this. Orange tabs if you didn't.
I'm not getting the last one. I got the first number that you had. Oh wait.
Yeah, there it is right there.
Do we have a 6 point?
Oh, that was the average. I was showing people how to get the average. But I had just named my average, and I think in class last time I didn't give it a name. I just calculated it. I like giving things names because then you can just do math on the names later. You don't have to remember the numbers. So this is the confidence interval based on a sample of 30 draws from a deck of cards. So the reason that I went down this path was thinking about this way of thinking about a confidence interval. One way of thinking about this confidence interval is that somewhere within this range lies the true population value. Well, we know what the true population value is because we have a very simple population, a deck of cards. 4 suits of cards, each card has the same numerical values in it. From 1 to 13, the average of the sum of the values from 1 to 13 is 7. So we know what the population mean is. The population mean is mu, and the sample mean is an estimate of mu. And in this way, thinking about the confidence interval in this way works perfectly fine because this is the estimate. It's not exactly what the population mean is, but the confidence interval on either side of this includes what we know to be the population mean. This is exactly what, in theory, the combination of the central limit theorem and the empirical rule is supposed to be doing for us, if we are interested in estimating the population mean. Now, if we didn't know what the population mean is, the population mean could have been as high as 7.73 or 7.74, could have been as low as 4.996, or it could have been anywhere in between. We just happen to know what it is in this case. One of the few examples in the world where you will actually know the population mean. But the empirical rule and the central limit theorem is working. But the central limit theorem is way more powerful than this because the central limit theorem basically says something about if you go to this population of cards over and over and over again, it will give you a distribution of sample means that is normally distributed, regardless of the original distribution. What's the shape of the original distribution for a deck of cards? Is it a normal distribution? No. It's what we call a uniform distribution. Same number of representatives of 1, 2, 3, 4, 5, 6, etc. There are 4 1s, 4 2s, 4 3s, 4 4s, 4 5s. It's a uniform distribution. It looks like that. It's just a big block of cards. But what the central limit theorem says is if we go to this block of cards, what we won't get out of this when we sample over and over again, we won't get a distribution of sample means that is a block. We will get a distribution of sample means that is a normal curve. The bigger the sample, as we get closer and closer to 30, the narrower that distribution of sample means becomes, because 30 cards gives you a lot better view of the deck of cards than a sample size of 2. So what we did initially, way back when we started this, was we went to the population and we drew 2 cards out. In some cases, we got close to the actual population mean with a 7.5, a 6.5, but in some cases our mean was pretty far off. 1.5. That's not very close at all to the population mean. And the thing of it is that because this was a 1 and this was a 2, the amount of variation between those two numbers is going to be really small, which means that the confidence interval is going to be relatively small. But because we have only 2 observations, we have 1 degree of freedom, the t statistic is going to be really big. It's going to be something like 12. So we would, and we can go and see what that actually is. Let's go find what the t statistic is for a sample size of 1, or for degrees of freedom of 1. Oh, it's 12.7. So let's do some calculations really quick. 1 plus 2 is 3, which means the mean of that is 1.5, 1.5, 1.5, minus 1 minus 2. This is 0.5, 0.5. Each of these squared is 0.25, 0.25, which adds up to 0.5. 0.5 divided by 1 degree of freedom is 0.5. So sample variance is 0.5. What's the square root of standard deviation? Is the square root of 0.05. What is the square root of, what is the square root of 0.05? Somebody do the math real quick. Actually don't know it off the top of my head. 0.7071, something like that. Okay, so that's the standard deviation. The standard error is 0.7071 divided by the square root of 2. What does that turn out to be? I don't have my calculator or my phone or anything, so help me with the math. 0.499. Okay, so that's the standard error. So we'll just round that off to 0.5 times 13, which would be 6.5 approximately. So the mean here is 1.5, but the confidence interval is basically plus or minus 6.5, which means it could go up as high as 8, but then it goes down way below 0, whatever 6.5 minus 1.5 is, which is minus 5, right? Yeah, to positive 8 to negative 5. That's the range of that confidence interval. So here we have a different estimate of the mean of 1.5 that falls outside of that confidence interval, but it goes all the way up to 8 and all the way down to negative 5. Does that confidence interval encompass the population mean that we know what the population mean is? Sure, it's 7. It's up here. But it's a really terrible estimate. of that population mean because it's based on only 2 observations. So because it's a really terrible estimate, because it's only based on 2 observations, the confidence interval to capture the population mean has to be really, really big. And we would like to do a better job of estimating the population mean if that's our goal. So what we did instead, though, is rather than just sample that population once with 2 observations, we sampled it 15 different times, 2 observations each. Let's redo all these calculations on those sample means. Okay? So how I want you to do that is, we've already done some coding work, so let's go back into R. Give ourselves a little space. Make yourself a note. Okay, so we're going to do all those same calculations that we did before, but now we're going to do them on the sample means. So the first thing we have to do is we have to remember where our sample means are. And as it turns out, our sample means are in the data frame that we called DAT earlier. So let's make sure that that's the case. We have a data frame that has the original data in it in the 15 trials of 2 draws each, and the average values for each of those trials is in the column X bar. Okay? Everybody see that? So go back up to all the calculations that we just did, starting at average. And then we're going to basically just copy all of that, and we're going to paste it down here, and we're going to just have to change some things. So what we're going to first have to do is we're going to have to change the average, because we're going to calculate the average differently. Because what we're doing is we're taking an average of the column that is the X bar column of that vector. Okay? So notice that I'm commenting things out so that I myself know what I'm doing with this new set of data. Yeah.
So, as opposed to calculating a sample mean, or like a confidence interval the way we did just now,
We're doing it based on the averages of the individual trials. So before, the first time we did it, we said we have 30 values.
Sure.
And so we're just calculating the mean and the confidence interval based on those 30 values.
Now we're at 15.
Now we're going to calculate the variation of 15 samples of size 2, those averages.
So
Yep.
15 different samples.
15 different trials, each of sample size 2.
Okay.
Yep, exactly. And hopefully you'll see the point of all of this when we get to the end of it. Everybody get their average calculated? Check it to make sure that it did it. Whoop. So, whoa. No, that did not do. Oh, I forgot something. I need to take the mean of that. My bad. Does that work? Yeah. Sorry, I forgot to take the mean. I just got it to reproduce the averages that we had done before. So take the mean of that column, and it should give you 6.36. All right, everybody there? We don't need to make DAT2 because that was what we were doing to combine the two raw data sets. So we can just delete those. But now we need to get the sample variance. So what we need to do is we need to take this sample variance equation, and we need to tailor it to this new thing that we're doing. So we don't want the sum of dat2, we want the sum of dat $ x bar minus the mean, minus really average. In this case, we've actually given it a name, average. Square that, and we want to divide it not by 29 now, but divide it by 14 because we have 15 sample means that we're working with. And I got 6.15, see if that's what you guys got also. Yeah.
I got 0. Some dat
Okay.
x bar.
So you got the average?
Oh, sorry, it's touchscreen.
Yep.
My bad.
All right.
So we have
X bar, not X var.
Oh,
BR.
yeah.
Yep. Spelling. Spelling matters. Always. Yeah.
What should I have done?
Whoa. Oh, that's weird.
Isn't that what you have?
That is what I have.
Check you.
Did I not run mine? Oh yeah, I have 6.15. All right. That's weird. Ah, you're missing some parentheses.
Okay.
You need a parentheses that groups all of that up to the square.
So right here. Okay, yeah, I see.
Actually, yeah.
It's
See,
right
compare this one to that one. Yep, exactly. Now run that. It's an order of operations thing.
Yeah,
There it is. Yep. Yeah.
So for some reason, like, I got the mean and stuff right here, but for some reason I don't have the same, like, average and all that stuff. Yeah, I don't know why.
What do you mean?
But,
So that's the same average.
yeah. Maybe you're
Okay.
using different.
So what I need you to do is copy all of this from sample variation down.
Yeah.
Copy all that, put it down here. Well, sorry, no, copy all of it, and then put it down at the bottom of your pane down here.
Just a simple bar?
No, all the way down to the calculation of the confidence interval.
Oh.
Yep, all the way through there. Yep, copy that. Now paste it right down here, and then start editing that. So now you can just take this thing that was already kind of done for you.
Yeah.
It's this line here that has the full thing.
Yeah.
You change that to dat $ x bar, and that to average, and that to 14.
Okay.
Yeah. I saw Red say, oh, you figured it out. Okay, good, awesome. Run back up in your output. Let's do a comparison on the board. What was the sample variation for sample size of 30? What'd you say? 13 point? What is it here? There's a lot more variation in this data set than there is in this data set. Part of that reason is because we're now calculating the variation among sample means. And one of the things that happens is that when you look at the distribution of sample means, the distribution of sample means is always narrower than the original population that you're drawing those sample means from, because they're more closely centered to the middle, which is what makes that thing turn into a normal distribution to begin with. Okay? Everybody with me? Let's do standard deviation. Standard deviation is easy because now it's just the same as it was before, because we've named this sample var. Wait, what's going on? You guys get 2.48? What was it before within 30? Okay, so once again, the standard deviation is also smaller, once again because we're doing this on a sample of sample means, not the raw data themselves. Now we have to change the standard error because it's now going to be the standard deviation divided by the square root of 30. And it really should be square root of 15 in this case. And I don't know why it keeps doing an average at the end of everything. And so now the standard error is 0.64, and it was what before? The t-statistic in this case was 2.045, and this was for 29 degrees of freedom. But now we have 14 degrees of freedom. So fewer degrees of freedom. What is the t-statistic for 14 degrees of freedom? Yeah.
2.145.
2.145. So they're not really that different, are they? So to get the magnitude of the confidence interval, we multiply the standard error times the t-statistic, which is what we did before. So we have to, yeah? 14 degrees of freedom, it's always 1 minus the sample size. So this is now 2.145. So the confidence interval, the magnitude of it is 1.3745. What was it for the sample of 30? Was it 1.37 also?
1.3708.
1 point. That's not what I remember getting earlier. It is what I got earlier. So now let's do the upper limits and the lower limits. And it's 7.74, 4.99. So they're basically the same size, which is not what I found when I did this earlier. Why is that the case? Have I done something wrong? Unfortunately, I didn't print out my outputs. Is everybody getting the same thing? Yeah.
So when you name something, how do I know it's not pulling
You have to run that line again down here. So for example, because we calculated sample variation with a different calculation, when we run that, it gives us the new value, as opposed to if we go back up here and run sample var up here, it'll give us that same value. If we want it to give us that sample variation, we have to run that equation again. Okay, does that make sense? So these scripts are just like programs in that they're linear. So if you do this naming where you name things the same thing over and over again, you have to, if you want to go and retrieve the other thing, you have to go back and run that. One way of avoiding that is we could have gone through and done all of this, like average 1, sample variation 1, standard deviation 1, standard error 1, etc. But then we would have had to have changed this to average 1, sample variation 1, etc., etc. And then you would have discrete names that correspond to the different portions of your script. So it becomes a preference thing, how much you want to keep track of that throughout a script. In some cases, it's really good. So we had some difficulties. The first time we were going through this, in that we created 2 data frames, and I named both of them DAT, and then somebody tried to go back and do something from the first portion of stuff, and it was giving us the second portion of output. It's because we had to go back and reload that data frame again to get the answer for that first part of stuff. So it just depends on how you're going to go about structuring your R scripts. I will oftentimes, if I have multiple forms of a data frame, I'll do .1, .2, .3, and then I just know that if I'm going to copy something from up there to down here, because I applied that to .1 and I want to apply it again to .2, all I have to change in that later code is the data frame name. And it'll do everything again, but I have to remember that in the process of doing that, I overwrote everything that I did up there. So if I want that back again, I have to rerun that. Does that make sense? So having gone through this, you see that you get very similar values. And the reason that you get very similar values is that in the one case, you have a much larger sample size. As a result of a much larger sample size, you end up having data that are more variable, but when you go to calculate the standard error of the mean, you divide that more variable data by a larger sample size, dividing by square root of 30 versus the square root of 15. And then that brings these standard errors much more closely in line with one another. And you'll also notice that the t-statistic doesn't really change very much. Going from a sample size of 15 to a sample size of 30 doesn't gain you a ton of statistical power. It reduces the size of the range that you have to look at a little bit, but it's only a tenth of a point in terms of a tenth of a standard error. And so gathering 30 data points versus 15 isn't nearly as big of a deal as gathering, so that's doubling sampling effort, going from 15 to 30. That doesn't gain you nearly as much as going from 7 to 15 in terms of the size of this confidence interval. So whenever you're thinking about this, you want to always be thinking about what is the sampling effort that I'm putting in. 30 is a good rule of thumb. Let's just go and look at this. One day we will get to chi-square test, I promise. Sample size of 1 to 2 to 4 to 8 to 16 to 32. This is a doubling of sampling effort. The t-statistic for 1 is 12.7, sample size of 1, sample size of 2 is degrees of freedom 1, 4, 8, 16, 32. We'll just make this 30 because that's what it goes up to. This is degrees of freedom 1, degrees of freedom 3, 7, 15, and 29. The t-statistic for this is 12.7. This t-statistic for a degree of freedom of 3 is 3.18. Degrees of freedom for 7, 2.36. 15, 2.13, and 29, 2.045. So very quickly, in terms of ramping up your sample size, you get to confidence intervals that are considerably narrower than when you have very few samples, and the change in the width of that confidence interval doesn't really change that much based on the t-distribution. A huge jump moving from sample size of 2 to sample size 4, a considerably lesser jump going from 4 to 8, another doubling, an even lesser jump going from 8 to 16, and then hardly any jump at all going from 16 to 30. My professor in grad school said sample size of 30 is a lot closer to infinity than it is to 0, and this is the reason why. We sample populations partly because we want to know what the population mean is, but more often than not, we want to know whether another mean that we collect could have come from this population that generated this confidence interval, or did it come from another population? If we have this confidence interval and we generated another sample mean of 1.5, we would have concluded that this 1.5 came from another population because it doesn't fit within this 95% confidence interval. So a lot of times students make the mistake of thinking that the way to look at confidence intervals is if you have a mean and a confidence interval, this is mean of sample 1, and you have another mean from sample 2 and a confidence interval, a lot of times students think, oh, these two means are not different because their confidence intervals overlap with one another. But that's not the question that you should be asking. Confidence intervals are asking the question of inclusion. Is this mean included in this confidence interval? Is this mean included in that confidence interval? If this mean is included in this confidence interval, then it's likely that that mean came from the same population as this mean. If this mean is included in this confidence interval, it means that that mean likely came from this confidence interval. Because 95% of sample means fall within this range. Now, this could be in the 5% that is a part of this population that falls outside that range because we set a 95% confidence interval on this. But there's only a 5% chance that it's out there. Similar fashion, this could be in the 5% that is in this tail. Over here, really only the 2.5% that is in this tail. But once again, because that's only 2.5%, that's a relatively unlikely occurrence. If, on the other hand, this mean and its confidence interval looks like this mean is included in this other mean's confidence interval. This mean is included in this mean's confidence interval. You could say that this mean came from a different population than this mean came from, but chances are you're going to be wrong. Your chances of making a type 1 error are high because to get this one to not be included in this one's confidence interval, you would have to really reduce the size of that confidence interval. Well, how do we reduce the size of confidence intervals? We reduce the alpha level. We were testing at a 0.05 level. Now we're testing at a 0.1 level, which is an 80% confidence interval, which means that there's 80% of sample means in here, which means that there's 10% of sample means out here and 10% of sample means out here. And so you could say that this mean is different from that mean, but you're going to reach that conclusion incorrectly 20% of the time, as opposed to reaching that conclusion incorrectly 5% of the time. So the alpha level, the type 1 error rate that you choose, will determine how big your confidence intervals are. That will determine your ability to tell two means apart. It's way easier to tell two means apart at an 80% confidence level than a 95% confidence level, because you're willing to make a mistake in that determination 20% of the time versus 5% of the time. And so that then affects how wide the confidence intervals are, and it affects whether or not you have inclusion. So an important thing from this first set of material is understanding what the central limit theorem does, relates populations to sample mean distributions. Those sample mean distributions are normally distributed, which means we can then apply the empirical rule. But the whole reason that we're applying the empirical rule is so we can make decisions about whether two things are different. And we do this far more often, trying to see if two things are different, than we do this, which is saying, how well does this estimate the population mean? We hardly ever do that. We do that all the time. So when we do this, the question isn't a question of overlap. It is a question of inclusion. Is the mean included in the confidence interval of another mean or not? If it's included, they're not different. If it's not included, they are different. Okay? So think of it as inclusion rather than overlap of confidence intervals. Super common mistake. Takes you a long time to get out of that habit if you picked up that habit from high school or something like that. Questions? Yeah, and I'll have that up today. I've got it done. I just need to check the R script to make sure the R script runs correctly. But all the rest of it. You've got some playing with cards, dealing with these ideas, looking at the uniform distribution, doing some sampling of the card deck yourself. Then the R script takes you through sampling that card deck at larger and larger sample sizes. Then I have a couple of problems where I ask you to look at data and calculate confidence intervals and make decisions about the means and things like that. Once again, just to get you through the mechanics of this, I want all of those things done by hand. I give you space in the worksheet to work those by hand. Once again, the reason I want you to work them by hand is that you learn how to do this. You learn how these things work by doing them by hand first. And in order to really cement it, you need to do it by hand often enough. When you guys saw me doing this, did you guys follow what I was doing? I went through it lickety-split, didn't I? Why? Because I've done this a gajillion times. The more often you do this, or the more often you do this by hand, the more it just becomes kind of second nature to you. Yeah.
So for the homework that's going to be posted, we're not going to be putting anything into R.
You're going to be running an R script that I've prepared for you that gives you some output that I want you to look at and comment on, but you're not going to be doing any of the calculations in R.
Right.
Yep. All right. Questions? All right. Stickies. What went well today? What didn't go so well today? Put them up here on your way out, and I will see